Welcome back to Missouri Caves and Speleology. I'm Toby Dogweiler, and today our topic is going to be karst hydrology. Um, on the PowerPoint slide, I show a cave entrance that's actually in Kentucky with several students of mine that we visited a few years ago. If we zoom into that a little bit, what I wanted to point out here is the cave is transmitting water. So the purpose of the cave and the landscape within the karst landscape is to transmit water through the subsurface. Many systems, as we can see here, we have a student up there in the upper left. He's in one cave entrance. We have another student in the orange down in the center, and he's in a place where water gets swallowed and goes back underground. So in this situation, there's a possibility that water could come directly out of one cave, move briefly across the surface, and go back underground through another cave system. It's actually not all that uncommon. But what you also notice here today, or at the day this picture was taken, is there is no water. There's no water moving through this part of this system. These are all overflow routes. So karst hydrology can be very complicated with different routes that are active at different water levels. Big rainstorms may activate routes that on normal days, normal dry days, don't have any water in them. So I'm going to take us back and revisit something from an earlier lesson just to bring us all back up to speed on what the definition of a karst is, what the definition of karst is. Traditionally, the definition has been something like karst is a specific surface landscape with distinctive hydrology and landforms. We discussed earlier that Klimchak and Ford in a 2000 publication tried to broaden that definition to bring it up to date with better understanding of these systems to incorporate the idea that the essence of this karst system is that water circulates underground, creating caves because the rocks are soluble. So because the bedrock can be dissolved, because the limestone or the dolostone that lots of these caves form in can be dissolved by the water, it naturally carves these pathways right through the bedrock. Before we get into karst hydrology, I want to talk a little bit about what this word hydrology means. Maybe most people know this, but just to make sure we're all up to speed, hydrology is simply the study of the movement of water, and it can mean different things in different disciplines, but it always has something to do with moving water. In karst, this study would include both surface and subsurface waters. In other parts of geology and engineering and geography, sometimes we'll separate surface water as hydrology and groundwater as hydrogeology. But in karst, those distinctions are blurred because water moves back and forth between the surface and the subsurface. So karst hydrology includes water wherever it is in the karst terrain. A basic concept of geology and groundwater science is the idea of an aquifer. So an aquifer is a subsurface zone with an earth material. That earth material could be bedrock, it could be unconsolidated sediments, for instance gravels or sands, that can store groundwater and then release it to humans in useful quantities and at useful rates. And those last two caveats are important. What constitutes an aquifer depends upon if it's useful to humans or not in that context. Obviously, if you live in a really dry area, something you may consider something an aquifer. It may serve a useful purpose for you, and in another wetter part of the world, we might not even consider that formation an aquifer because it doesn't yield much water or at a useful rate for another purpose. Another term that we need to all understand is the idea of porosity. So porosity would be the amount or number of voids, which we can also call pores, in an aquifer. So we're talking about the empty spaces within a body of bedrock or between individual sand grains or gravel grains if we were in an unconsolidated aquifer. The porosity gives an indication of the aquifer's capacity to store water. The more porosity, the more water that aquifer could hold. Now limestone as a bedrock typically has a very low primary porosity. And what I mean by primary porosity is the porosity that formed along with the bedrock itself. So the initial limestone bedrock after it forms doesn't have much porosity in it. Permeability is the ability of water to move between pores within an aquifer. So this is essentially a measure of how well connected pores are. Some bedrocks or aquifers may have very high porosity, but the pore spaces may not be physically connected, or at least all that well connected. And that means they can store water, but water can't move from one pore to the next, which means you can't get water out of that aquifer very easily. So high permeability indicates the ability of water to move rapidly through an aquifer. We're going to come back to this idea throughout the discussion today. On the right side of the PowerPoint slide, you'll see a blow up sort of some sand grains or some grains in a sandstone perhaps. And you can see that some of those pore spaces, the spaces between where those grains can't quite pack perfectly together, some of those are air-filled and some of those are water-filled. Now the boundary between those two types of pores, water-filled and air-filled, is called the water table. So the water table is the boundary between the pore spaces that are unsaturated and the pore spaces that are saturated. So it's the boundary, in other words, between the pore spaces that are filled with water and the pore spaces that are not filled with water. It doesn't mean that the pore spaces above the water table don't have any water, they're just not filled with water, they're not fully saturated. Two more terms we need to define, and these are important in karst. The vadose zone, this is the portion of an aquifer, or for our discussion today, a cave system above the water table. So this is the vadose zone is the part of the karst system that's above the water table. The phreatic zone is the portion of the cave system that's below the water table. In non-karst aquifers, this would be above or below the water table, the pores above or below the water table. All right, so before we delve fully into karst aquifers, this is a non-karst aquifer, typical aquifer in many parts of the world that doesn't have karst. And what you see is the phreatic zone is the saturated. It's saturated as indicated by the blue, indicating filled with water, part of the land. And the unsaturated zone, or the vadose zone, which is above the water table, so where those pore spaces are not saturated. One thing I want you to take from this diagram is the idea that water tables aren't completely flat. They generally, sorta, kinda, mostly follow the topography of the landscape. So you see that as that hill rises up from the stream, the boundary of the water table does too. You'll also notice that the surface water stream, so the stream that we're seeing in cross-section there, is an expression of the water table. It is directly connected to the water table, and on days when it's not raining, maybe when it hasn't rained for a while, all of that water that's flowing in that stream is being fed slowly and diffusely from the groundwater. That's what maintains flow in our streams or our cave systems even when it's not raining. Here's a block of limestone. Now I mentioned earlier that limestone typically doesn't have much porosity, or primary porosity that forms when the rock formed. But after that rock forms and it gets exposed at the Earth's surface to rainwater, and we discussed this in an earlier lesson also, that rainwater starts to attack the limestone and dissolve it. And the easiest place for the water to attack the limestone and dissolve it is along the natural joints and fractures that occur in the limestone, as well as the bedding planes. So joints or fractures, these are terms we use to describe sort of vertically oriented cracks in the limestone. Limestone, or any bedrock, is not unlike the concrete in your driveway or on your sidewalks. Generally you have a big block of brittle, rigid material sitting there. Eventually differential settling of the things underneath of it start to cause cracks. Just like you get a crack in your driveway, you'll get these cracks in the limestone. Well, those are pathways. That's the pathway of least resistance for the water to move through the rock, because there's not much primary porosity. and then those become enlarged, and they can become enlarged into caves. And this diagram attempts to portray that we have different fractures and joints in the limestone that have become pathways for water to move through. The fractures and joints that can move the most water become the biggest, the fastest, because the more water they can move through, the more dissolution that water can create, which creates space for more water to move through, which causes even more dissolution. So it's a classic positive feedback cycle. Here's a picture of a limestone outcrop where the soil's been stripped away by erosion processes, and this reveals to us what these actual limestone looks like out there in the quote-unquote wild, if you will. This is a limestone that's been attacked by solution. You can see that there are fracture patterns that are running sort of into and out of the screen and then from left to right to create these big blocks of limestone. Some of those fractures have become larger than others. They're able to transmit more water, and then they become larger, as I discussed, and eventually all this water can be funneled down and concentrated into the most dominant fracture, which then can form into a cave because it becomes so dissolutionally enlarged. So if we think about the way then that water can move through a karst system, there are really three different pathways it can take. The first are the pores, but like we said, most limestone, most dolostones, most rocks that karst forms in don't have much in the way of primary porosity. So most of that porosity then, most of the pathways that water can follow through the limestone are secondary porosities, the joints that form after the bedrock forms, or the caves that form as those joints and fractures get enlarged into bigger and bigger passages. So we can separate this out as pores, joints, and caves. These are the pathways water can take through our karst aquifer. Here's a diagram we've looked at in previous lessons also. It shows a generic karst system. And what I want to point out here is this red line. I'll flash it a couple of times. The red line is the water table in this diagram. So we have some cave passages above that red line, and we have some cave passages below that. We can label those cave passages as either vadose passages, which are the ones above the water table, or phreatic passages, which are the ones that are below. And these passages have very different morphologies or shapes to them because they form in different places. In the vadose zone, most of what the water is trying to do is move vertically towards the water table. As water, you can see the rain falling on the landscape in the top of the picture. That water, as that rainwater becomes soil water and then moves into the bedrock, starts to move through these fractures and joints and bedding planes, it's trying to get down. It's trying to get down to the water table. And so vadose passages tend to be vertically oriented. Once it gets to the water table, a different set of forces control the movement of the water, and these forces result more in a tubular passage or a tubular cross-section passage, so maybe more round or oval shape. So let's look at a couple of pictures. First, here's a vadose passage. You can see that the person standing there gives some sense of scale. The passage is narrow, but it's very tall. That's because the water is not going to waste its energy dissolving the passage wider. It wants to dissolve downward to get to the water table. So that's a vadose passage, and it's vertically oriented. Here's a passage in the Mammoth Cave system from Kentucky. It's a large phreatic passage. I don't know if there's a person in that picture for scale, but this would be something you could easily walk through. So it's quite a large passage. You see that it's got that tubular or oval cross-section. This is a classic phreatic passage. Often these phreatic passages will meander back and forth, and they're a good indication of where the water table was when this cave formed. Now, of course, since somebody was standing there to take a picture in this passage, this phreatic passage is no longer below the water table. forces have moved it up out of the water table, or the water table has dropped because climate changed or other external factors, and now this phreatically formed passage is exposed in a vadose environment, a non-saturated environment. But nonetheless, when we talk about vadose and phreatic, we're really focused on what mechanisms formed those passages, whether they formed above the water table or below the water table. And finally, this is an example from a cave in south central Missouri that I really interpret what's going on in this point in the passage where the person is standing as the transition from vadose to phreatic. The vadose part of the cave is sort of behind the person where the photographer is standing. And that was a much more vertically oriented, narrower passage. But then you come into this big room, and as you go down toward the bottom of the room where the person in the photograph is facing, you see that more tubular cross section. It's not the perfect oval like the previous picture, but it's a more tubular cross section. I think this is the area where we had the transition of water from vadose to phreatic in this system when it was actively forming. So the question I want to close with on this section is, should you drink that spring water? This is a question that I get asked a lot when I'm out doing field work in karst areas. Often I'll be measuring water quality or taking samples, and somebody will come up and say, hey, this is spring water, right? This is great to drink. The question is, never drink spring water, in my humble opinion as a karst hydrologist. One of the things we're going to talk about in the next couple of modules is that karst is very susceptible to pollutants because the water is moving through these very large pore spaces, the fractures and the caves. The water moves into the system and through the system very rapidly, which means that any pollutants that are washed into the system as that water infiltrates into the system have a minimal time to break down or be attenuated by other processes. So I think that the idea that spring water is super clean is either a very old notion or a notion that maybe has been propagated by marketers for bottled water. But in the real world here, spring water is very susceptible because springs are the outlets of these karst systems. It's very susceptible to pollution. And we'll talk more about that in our next module. So thank you for joining us on Missouri's Caves and Speleology, and we'll see you in the next module.